All right, last time we were talking about enzyme inhibition in the context of this model, which is the Michaelis-Menten model, plus two extra branches, branch that I call branch 1 and branch 2, that represent different kinds of inhibition of the enzyme. Branch 1 binds the inhibitor I to the enzyme itself, the otherwise unbound enzyme, free enzyme, and takes it out of action, basically. The EI complex is inactive, and so it just basically binds up some of the enzyme. There's effectively less enzyme in solution than there was before. And the other branch does basically the same thing, but with the enzyme substrate complex. So it takes out of circulation effectively the enzyme substrate complex, and that also stops product from being formed since the enzyme substrate complex is necessary. Last time we looked at one example, one easy example. Let's look at a more extensive example now. So example 2 here. And I just have some generic enzyme. We don't need to say what it was. It has these 4 parameters. So we're being given, in this case, all the parameters. And we're going to use those parameters to see what effect various concentrations of substrate and inhibitor have on the velocity of the reaction. So kcat is about 2,000 seconds to the minus 1, or 2,000 turnovers per second, 2,000 molecules made per second once the enzyme is saturated. Km is 10 nanomolar. That tells you that the enzyme will be saturated if the substrate concentration is much greater than 10 nanomolar, but also will be largely inactive if the substrate concentration is much less than 10 nanomolar. 10 nanomolar is, remember, the concentration at which you'll get half of the Vmax value for the velocity. Then the 2 Ki values are there. And notice I've chosen them to be quite different. So the branch 1 Ki is 100 nanomolars, which means you're not going to get much inhibition until you reach an inhibitor concentration on the order of 100 nanomolars. But the branch 2 Ki is 1 nanomolar, which means you're going to start getting significant inhibition at much lower concentrations at 1 nanomolar or so. All right, so let's pick some values. Let's suppose, first of all, that the enzyme concentration, the total enzyme concentration in solution, is 1 nanomolar. We only need that in order to calculate Vmax down here. Otherwise, it doesn't even appear. So that will always be the same in all the little sub-examples that we'll go through next. We choose the substrate concentration equal to 10 nanomolar. That's the substrate concentration where S is equal to Km. And therefore, we would expect 1/2 Vmax as the velocity if there were no inhibitor. And in this case, in fact, there is no inhibitor. We're leaving the I concentration at 0, so this is going to be ordinary Michaelis-Menten, uninhibited Michaelis-Menten. Just practice in doing a few of the calculations. We haven't actually plugged values into Michaelis-Menten before this, at least not in the lectures, so good to do one now. Here's the Michaelis-Menten expression with inhibition present. Alpha prime and alpha basically represent the extent of inhibition that's going on. And remember that alpha is equal to 1 plus the inhibitor concentration over the Ki value. That's branch 1 inhibition. And alpha prime is equal to 1 plus I over Ki prime. When alpha or alpha prime is 1, that means you're getting no inhibition of that type. So when alpha is equal to 1, you get no inhibition from branch 1. And when alpha prime is equal to 1, you get no inhibition from branch 2. And those are the cases where this formula reduces to simple Michaelis-Menten. And in this case, since the inhibitor concentration is 0, that's exactly what you get. Both alpha and alpha prime are 1, which means you get ordinary Michaelis-Menten. And we also have S is equal to Km, which means that you're going to get that V is equal to 1/2 Vmax. You can actually plug the numbers in here. This is 1 in this case, right? So clearly you get 1/2 of Vmax. we need to calculate Vmax. That's kcat, which is 2,000, times E0, which is 1 nanomolar. So 2,000 nanomolar per second is the maximum velocity. We're going to get half of that, and so we get 1,000 nanomolar per second. All right, going through that is useful, but that was all without inhibition. Now let's see what happens. Well, first, before we go into inhibition, let's see what happens if we increase the substrate concentration to 100 nanomolar. That's 10 times the Km value. It's not quite perfectly saturated, but it's 90-something% saturated, which means that our velocity is going to be more or less equal to Vmax. I didn't actually calculate the true value. It's something less than 2,000, but it's going to be close to 2,000. All right, part C then is when we're adding the inhibitor. In this case, we keep the substrate concentration high, so we're near saturation still as far as substrate is concerned. But now we're putting in 1 nanomolar of inhibitor, and that's equal to the Ki prime value. In other words, we're now in the range of inhibitor concentrations where branch 2 should be turned on, but branch 1 probably isn't. Remember, Ki for branch 1 is 100 nanomolar, and we're way below that. So branch 1 should be not turned on yet, but branch 2 should be. Also, yes, it's worth pointing out that Ki prime here, and also Ki for that matter, are Kd values. And when we were looking at binding, we know that if the ligand concentration is equal to the Kd value, then you're going to get your enzyme or protein or whatever it is half saturated. There's going to be half of the enzymes are going to have a ligand bound to them, or are going to be occupied. And so that's the situation we have here. We're in a situation where half of the ES complex, right, because branch 2 binds to ES, is actually going to be ESI. So we're taking out half of the ESI that's in solution. We're taking out half of the enzyme substrate ES that's in solution and turning it into the inactive ESI complex. All right, we calculate the alpha. We're going to need the alpha values in order to do our calculation down here. Let's calculate them. So for alpha, it's 1 plus I, which is 1 nanomolar, over 100 nanomolar for Ki. That's essentially 1. It's 1.01, but I'm not going to bother with a 1% effect like that. For alpha prime, on the other hand, we expect an effect because now I is 1 nanomolar, so is Ki prime. That means this is a 1. That means alpha prime is now 2, so it's significant. It's not huge yet. If we went to higher I concentrations, it'll get huge. We'll do that below, but it isn't huge yet, but it's still going to have a serious effect. Plugging the numbers in, alpha prime then is 2. Alpha is equal to, I'm just going to call it 1. Km is 10. S is 100, so we're nominally saturating. And that means that this denominator down here, this term is small, right? It's 1 times, it's 0.1. So that means this denominator down here is basically 2, which means we've reduced our maximal velocity to just half of what it normally is, as is expected by what we said up above about branch 2 types mechanism, right? Branch 2 lowers the Vmax even when you're at saturating conditions, but doesn't change the Km value. And you can see that here, right? Alpha is equal to 1. This is the Km value. Alpha times Km is still the Km value. It hasn't changed the Km value, but it has affected the Vmax. It's now half of what it was before. I mean, it's actually a little less than half here. That's the real number. But it's basically half of what it was before. So 1 nanomolar worth of inhibitor, in this case, was good enough to reduce the velocity of the enzyme by a factor of 2 because the Kd value for type 2, in this case, for branch 2, is really pretty low. It's the low Kd value for branch 2 that's causing branch 2 to turn on so strongly with relatively small amounts of the inhibitor. All right, case D here. we set the inhibitor concentration up to 10 nanomolar and don't change anything else. So we still are at nominal saturation in S. At this concentration, we have that the inhibitor concentration is 10 times bigger than Ki prime, so branch 2 is totally on now. It's well on. But the I concentration is still only 1/10 of the value of Ki, which means that branch 1 really still isn't on. We're in between the two cases. We've fully turned on branch 2, but we haven't really turned on branch 1 yet. Branch 1 is going to have a small effect now. It isn't 0, but it is going to be small. Oops. And so, calculating alpha prime and alpha prime is now 1 plus I concentration over Ki, which is 11, indicating that we're now, branch 2 is strongly inhibiting things now. But branch 1 is still 1 plus 10 over 100, which is 1.1. Okay, that 0.1 isn't 0. But we're still not we're getting a tiny amount of inhibition from branch 1, but still not much. Plugging the numbers in, here's alpha prime, here's alpha. You can see that the effective Km now is 11, right, rather than 10. And so it's a little bit harder to to saturate the enzyme than it was, but almost the same. And that gives a velocity, finally, of 180 nanomolar per second, which is about 10 times less than 2,000, right? Even less than 10, even more than 10 times less than 2,000. So we've reduced the maximum velocity now because we've got a lot of inhibitor present. We've reduced the maximum velocity by a factor of 10 without changing the Km very much. All right, now let's change the parameters, because with the original setup, we couldn't really turn on branch 1 without also turning on branch 2. And we want to see what happens with branch 2, with branch 1 alone. So let's change the parameters. I made Ki prime now huge, 10 to the 5th. So we're not going to be able to turn on branch 2 anymore. And I've made Ki smaller. It was 100, now it's 10. So we will be able to turn on branch 1, and let's see what happens. So we set the I concentration now to 100 nanomolar. That's 10 times bigger than Ki, so we're going to turn on branch 1 completely. And we're going to set the S concentration to 10 nanomolar. So I've turned the substrate concentration down a bit, right? So we're not saturating anymore. We're at half max. In the absence of inhibition, we'd be at half Vmax. Let's plug the numbers in. So alpha prime here is 1 plus I now over Ki prime, which is 1 plus 100, 100 for I, over 10 to the 5th, which is 1, right? That's 1.001, actually, 1 close enough to 1. But alpha now is 1 plus I over Ki, and I is 100, Ki is 10, so alpha is now 11. The effective Km is now 11 times bigger than the original uninhibited Km. And that means that it's going to be harder to saturate now. We have to put in 11 times as much S as we would have in order to saturate. We were going to half saturate if there weren't any inhibition, but now we're not going to be anywhere near saturation. And the way that turns out is if you plug the numbers in, V is equal to Vmax over 1 plus 11, which is 1/12, which is 167 nanomolars per second. We should have gotten about 1,000, right? If that's half of Vmax. If there weren't inhibition, in the presence of inhibition, it's gone down by, well, more than a factor of, about a factor of 6 from what it should have been. And so branch 1 has now caused not a 10-fold reduction, but a 6-fold reduction in the velocity of the enzyme. And that is it for this section on enzyme kinetics. We'll stop here and begin the very last section of the class now on molecular machines and how all this stuff applies to complex biological molecules.